This is lesson 6.4, the graph of y equals ax squared plus bx plus c, which is what we call standard form for a parabola. Okay, so we're going to build off of what we were doing in the last section with parabolas. We're going to have an original parabola, and then we're going to take that and we're going to transform it in some way or kind of move it around, and then we're going to get a new parabola. So that first thing there, parabola congruence theorem. So it says in the book, the graph of the equation y is equal to ax squared plus bx plus c is a parabola congruent to the graph of y is equal to ax squared. Okay, so what that means is if you've got the equation y is equal to ax plus bx plus c, that's going to be the same exact size as an equation that's y is equal to ax squared. So here, as long as whatever these first two things are with the x squared, so as long as you got it to y equals, and these letters here for a are identical to each other, that will mean the graphs are going to be congruent in shape. So basically, however big one is, the other one's going to be the same size as that, whether it's, kind of like that, or if they're like little skinny ones. Could be two little skinny ones or two fat ones or whatever. The A's determine that they have the same shape. The B and C stuff basically determines how we slide it around, and that comes from what we were doing in the last section. So the form we had from the last section for this was vertex form, where it was y minus our k is equal to a, so that same a from there, parentheses, and then x minus h to the power of 2. So remembering from the last lesson that k and the h basically tell you how far you're sliding it around in which direction. So the k determines your up and down movement, the h determines your right and left movement. So what we can do is we can take that vertex form from the last section and we can change that to standard form, which is what we're working with today. So basically if we kind of just solve this out here, so like add k to each side, and then keep going there and go, okay, well now we got a parentheses x minus h squared. Well, that squared just means it's that chunk times itself. Then if we do our FOIL business out, we get a times, that would be what it is, simplified FOIL down plus the k. Then what they do is they just combine all of that stuff together into one thing. What this is telling us here is if we were trying to put this with the b and the c, the b is coming from whatever we get for this, because that's got our x in it, and we know like our b in the formula always just has the single x. So whatever that is there, like -2 times whatever our a value was times whatever our h value was, that always goes with the x for the b. And then the c is actually a combination of a couple things. So it's a combination of whatever our a was times whatever our h was squared plus whatever our k was. So you would take those two, add those two together, and that would determine your c. Okay, I don't think you're going to have to do a whole lot of that where they just leave it with like variables like that, but that's where those numbers are coming from. Most of the stuff we do is just going to have normal numbers in it, like you'll see with the next problem here. Okay, so for our first example, it says show that the equation y plus 5 is equal to 4 parentheses x plus 3 to the power of 2 can be written in that form. Y is equal to ax squared plus bx plus c, which is our standard form. And then once we get it to that form, they want us to give the values of the a, the b, and the c. Okay, so I would just start with that equation there. So y plus 5 is equal to 4 parentheses x plus 3, and then that chunk squared. So the first thing I would do is I would probably get the 5 to the other side. This doesn't have to be your first step, but I'm going to start with it that way. So that way I've got like the y by itself here. Oops, I don't know why I'm adding 5. Should be subtracting 5. Subtracting 5 from each side, because then that'll make those guys go away. So then we'll have y is equal to 4 parentheses x plus 3, that chunk squared, and then the minus 5 just goes to the back. Like I said, you don't have to start with that step. You could do that step at the end, but I don't know. The book has it starting with that step, so we'll do that. Then what I would do is I would expand this out. So there was a formula that we did, I don't know, a couple sections ago that there's a pattern it always follows for squared. I typically just do FOIL because that's easier to remember. So I would go like y is equal to 4, and then I'd go parentheses x plus 3, that chunk, times that same chunk of x plus 3, because that's what squared means, is something times itself, and then minus 5. And then from here I would do my foiling out, so I would do like x times x for first, So here I'm going to write y is equal to 4, and then I'm going to go with big parentheses because the 4 has to be taken times all the stuff here for our FOIL stuff. So I'm going to go 4 parentheses. X times x for first would be x squared. Outside would be x times 3, which would be 3x. Inside would be 3 times x, which is 3x. Last would be 3 times 3, which would be 9. So plus 9. And then I'm going to close my parentheses because that's all my stuff that gets taken by 4. And then that minus 5 is just at the back there. Then in my parentheses, I would combine my stuff I can. So like there, I'd put my x's together. So 3x and 3x would make 6x. So y is equal to 4, parentheses still, x squared plus, I'm putting those two together to make 6x, plus 9, and then my minus 5 is still at the back. Then I would probably go through and do distributive property. So I'd take the 4 times all my stuff in parentheses there. So that would be like y is equal to 4 x squared. The 4 times the 6x would be 24x. And then the 4 times the 9 would be 36. And then I don't have to take the 4 times the minus 5 because it's not parentheses, so I'll just drop down that minus 5. And then my last step then would be to combine my two constants together. So the ones without x's, I would put the 36 and the 5 together to make 31. So my final standard form equation here would be y is equal to 4x squared plus 24x, and then those two together would make 31. So plus 31. So that would be in standard form. Then they want us to identify my A, my B, and my C. So my A is always, when I get to this form, whatever's with my x squared. So A is 4. B is whatever's with the x, so that would be 24. And then my C is always my constant when I'm in this form, which is the 31, which doesn't have any of the x's with it. So that would be the A, the B, and the C. Okay, next one here. Okay, so this one says, suppose a ball is thrown that has the height h is equal to negative 16t squared plus 42t plus 7 after t seconds. So h is height, t is seconds. We're supposed to find the h values when our t is 0, 1, 2, 3, and 4. Okay, so I would probably revert to my calculator here to do this. You could plug this stuff in by hand, it wouldn't be too bad. So like here, if I was plugging like 0 in by hand, put the 0 in for the t, so it'd be like 0 squared, 0 times negative 16 is just 0, 42 times 0 is 0, plus 7, so this one would be 7. Instead of doing that all out by hand though, you could do it by hand by plugging in that stuff. I'm just going to use the calculator because we've got it. So I would just go to my y equals, clear out whatever's in there, type in that equation there, so negative 16x to the power of 2 plus 42x plus 7, and I'd hit my graph. So you can kind of see parts of it there on the graph. If you want to make it so you can see that a little bit better, you could probably change your zoomer out a little bit. So you could either like zoom out, so we could do that, so just go to zoom out and then just hit enter once. And you can kind of see it there where it kind of goes up and down quickly. You could also change your window around too if you wanted to make it look a little bit nicer where it's, you know, more of the curve shape versus just like straight up, straight down. It doesn't really matter though, so we'll just leave it like that because we just need the table anyways for now. So I would just go to the table then. So I go second, graph button for table. And we've got the 0 at 7, which it shows that again there. And then our 1 is at 33. 2 we've got at 27. 3 is at negative 11. And 4 is at negative 81. Okay, so that takes care of our chart. Then it wants us to explain what the pairs mean, T and H, and what they tell you about the height of the ball for a T being 0, a T being 2, and then a T being 4. Okay, well T from up in our directions was seconds, and H was our height. I don't know if they tell us if it's in feet or... I think it's in feet. I don't think they say that anywhere. Maybe they do. I don't see it, but it should be in feet. So that would be height in feet. And then so explain what those ordered pairs mean. So the first one, 0 for the t, is 0, 7. So what that would mean, if our t stands for seconds, that would be 0 seconds and a height of 7 feet. So that would just mean at 0 seconds, the ball, because we're throwing a ball, the ball is, and it's a positive 7, so I'm going to put is 7 feet above the ground. So at 0, 7, that would be at 0 seconds, the ball is 7 feet above the ground. Okay, and then I'll do my next one there. So 2 would be 227. So same thing, t is the seconds, h is the height, so that would be at 2 seconds. The ball is, again, it's positive 27, so that would be 27 feet above the ground again. Weird R, ground. Okay, now this is where it gets a little tricky, because now for our 4, it's 4 and negative 81. So it's still seconds and feet, but if you think about like throwing something up and then coming down, to be a negative feet amount, it would basically be below ground level. So pending our situation, most of the time if our value here we get is below ground level, that's just gonna mean it's gonna hit the ground already and it's just gonna stop. Now technically here you could do some stuff with below ground level, like if it was like there was a hole in the ground or something, and this would be like 81 feet below the ground. For our purposes here, I'll just give both examples. So let's go at 4 seconds. The ball is 81 feet below the ground. So like I said, that would be like if there was like a hole dug or something and it went underneath the ground. And then I'm going to put just the ball has already hit the ground. So the other option is the ball has already hit the ground. If there's like no hole or anything for it to fall to. So, and most of the time you just put that it hits the ground. Most of the time there's not going to be like something where it goes below the ground or anything like that. So if it drops to the negative, it's just hitting the ground already. And you'll kind of see that a little bit from our graph here. So it says graph the pair, should be probably the ordered pairs, t and h over the domain of the function. So here, when we're doing domain stuff, if we're throwing a ball, we're never going to have to deal with a negative amount of seconds. So that's why it's only just like the positive number shown here. And then I'm just going to go out to maybe like 4 like I've got there. So like 1, 2, 3, 4, something like that. Maybe I'll go to 5 just to fill my line out a little bit better. But that would be my t for my time. And then my height's going to get pretty big numbers there. So I think maybe I might count by tens. Just put them kind of close together. So like 10, 20, 30, 40. Let's just go up to 40 there because our highest is 33. So I'm going to go 10, 20, 30, 40. And that's our height that we're measuring there. And then for our other way, we're going to have to go down to about negative 81. So I'm going to count by tens going that way. So negative 10, 20, 30, 40, 50, 60, 70, 80. So I'll fill those in. Okay, and then we'll just graph her out here. So if we're graphing this, our first one there is at 0, 7. Get that eyeballed in there. 1 is at 33. 2 is 27. 3 is at negative 11. And 4 is at negative 81. Oops, bad dot. Okay, so then I just kind of sketching my curve there. It's kind of hard to get the curve here exactly perfect, but just get it the best you can. I don't know exactly where it peaks out there, but we'll just kind of do something like that. Get my numbers spaced very good here. Something like that in general is probably fine. I made my line bad there. But something like that would be okay. So like I said here, when we're doing this, this is where like we're throwing it from. So probably throwing it from like 7 foot in the air because that was our initial height. Then it kind of goes up there, and we know when we throw something, then it's eventually going to come back down because of gravity. So somewhere in here, probably between the 2 and the 3 is where it's actually going to hit the ground. So maybe at like 2.8, 2.9 seconds, and we can actually figure that out from the calculator if we needed to. But basically, that's where it's actually hitting the ground. And then, like I said, pending the situation, you could go below the ground if you were, you know, like, I don't know, there's a hole or a canyon or something that you're going below, like ground level. But most of the time, we just say it hits the ground at that point. And then, you know, all the stuff from that, it's just already after it hit the ground. So now the next thing here, for part D, it says is the ball moving at the same average rate between 0 for T and T being 1, and T being 1 and T being 2. Okay, so to figure out rate of something, that's basically like kind of like the slope between those specific points. They just don't call it slope because it's on a curve versus just like a straight line. So here between T of 0 and T of 1, 0 is at 0.7, 1 is at 133. So we'll figure out our rate or kind of like our slope with that stuff. And then the other one, the T kind of is up there, but it would be between 133, and then they want it for 2, so 2 is 27. So 227, and then we'll figure out what the rates are at each of those. So here, like I said, it's kind of like the slope where it's like y minus y over x minus x. They just call it rate when it's on curved lines. So our y's here would be like the 7 and the 33. So if I go like 7 minus 33 over, if I chose the 7 first for my y, x has got to be the 0. So 0 minus 1. So figure out what that is. So if I just go on my calculator, 7 minus 33 would be negative 26. Over 0 minus 1 would be negative 1. So that would be a positive 26. And what we would be measuring in here, our y's was our like height, so that would be in feet. Our t's were in seconds, so it would be feet over seconds. So this would be 26 feet per second for that speed or average rate at that time. And then we'll do the same thing, a little line here. We'll do the same thing between these guys. So again, we'll do y minus y on the top, so it would be like 33 minus 27 over, and then because I chose the 33 first, I got to choose the 1 first, so 1 minus 2. So if I do that out, 33 minus 27, would be, I don't know why I was using the calculator, it's just negative 6. And then 1 minus 2 would just be negative 1. And then negative over negative, not negative 1. What did I do wrong here? Oh, that's a positive 6. Sorry. Positive 6 there. Negative 1 there, so it would be a negative 6. And then again, when we're doing it here, our h is in feet, our t is in seconds, so that would be negative 6 feet per second. And then basically the question was asking us, okay, is the ball moving at the same speed at those times? Well, if this one was a positive 26 feet per second because we were going from 0 to 1, so that was uphill, then when we go to 1 to 2, we're going on the downhill slide. So if that's positive and that's negative, they're definitely not going at the same speed, and those numbers aren't the same either. So I would just say no on that one. So they would not be going at the same rate there. All right. Next thing we got here. So this next thing here is an important formula you're going to want written down in your notes. So this here is the quadratic equation for the height of a projectile Projectile is basically when we just like throw something. So it's kind of like we just had in that last problem. There's a specific formula that we use or an equation that we use every single time with projectiles that'll kick out like how high it is after so many seconds, okay? So that equation here, and like I said, this is going to be important for your notes, is h is equal to negative a half g t squared plus v naught times t plus h naught. Okay, so let's talk through what those parts are. So h is always going to be your height at whatever time t you plug in, so h is height. The g stands for acceleration due to gravity. Now, pending what we are using as our label, if we're measuring it in feet, you always want to use 32 in there for the gravity. If you're measuring it in meters, you always want to use 9.8 as your gravity, and those just go into those spots, so it's different depending on what you're measuring in. T always just stands for our time in seconds, so it'll go into that spot there with the squared. Also that spot there is both time in seconds. The V with the little sub-zero there, that's called V naught. So I've got that written here. V naught basically means initial velocity, or like the speed that you're starting at. So whatever speed that you're starting at, they'll call that initial velocity. Initial velocity goes in the spot of V naught is what that's called. And then the last one there is h naught. So again, it's like the h with the little sub-zero there. That's pronounced h naught. That's always your initial height. So your initial ones are the ones with those knots there. It's kind of like it's starting at 0. And then that's always whatever your starting height is or your initial height. And those pieces of information they'll tell you or they'll ask you to find those. Okay, so let's do one here then where they're making us come up with the equation based on that equation there. So it says basketball player throws a ball with initial velocity of 48 feet per second from a height of 5 feet. Find an equation of the height of the ball after t seconds. After how many seconds does the ball hit the ground? Okay, so let's start with that equation there. So what do we have here? We got initial velocity is 48 feet per second from a height of 5 feet. So if that's our initial velocity at that height, that would mean that 5 is our initial height. And then we're supposed to find an equation for the height of the ball after t seconds. So we're just going to have a t in there and an h in there. And then we'll do some solving. Okay, so when we set this up here, we're going to go h is equal to, because we don't know the height, negative a half times our gravity. So here, since we're measuring in feet, we're going to want to use the 32 for our gravity. So negative a half times 32. And then t is another thing we don't know because that's our seconds. So t squared plus, next one is v naught. V naught stands for our initial velocity, which is the 48 feet per second. So 48, and then that's times our t. And again, we don't know what our t is, so we'll leave that in there. And then the other thing we know is our initial height, which is the last one. So h naught is a height of 5 feet. So that would just be plus 5 at the back for our initial height. Then here for your actual equation, I would probably simplify this down. So I would probably take the negative a half times the 32, which would be negative 16. So h is equal to negative 16 t squared plus 48t plus 5 is probably the equation I would go with for like finding the equation for the height of the ball part of this question. Then what they want us to do is they want us to figure out after how many seconds, so that would be our t, find our t for when the ball hits the ground. Well, when the ball hits the ground, that would mean it's a height of 0. So basically what we're going to do here is we're going to take the h and put a 0 in for that. So 0 is equal to negative 16 t squared plus 48t plus 5, and then we're going to solve that for the t. Easiest way to do this in a situation like this is to think about it like as a graph. So if I've got a graph here, I got somebody throwing this basketball from 5 foot, so they're starting 5 foot in the air, or 5 foot in the air off the ground. Throwing that ball, who knows how high or whatever it's going, but then it's coming back down and it's hitting the ground. Our goal is to figure out after how many seconds that hits the ground or the height is 0. So if I use my calculator, I can graph this out and then I can see where that spot is where it hits the ground, and I can use my calculator to find that. So that's what I'm going to do. So I'm just going to go back to my graphing screen here, get rid of that stuff. type in my equation here. So negative 16x power of 2 plus 48x plus 5, grapher. And I still got it zoomed out from before. So again, it's zoomed out pretty good. It would probably look more like that if we zoomed it in a little bit closer. But again, we just need the spot where it hits the ground, so it's not that big of a deal. So here what we're going to do is you're going to go to your trace button. So second trace, because we're going to calculate. And we want to calculate the 0 value here because our height is 0. So you're going to go down to that second one for 0. And then what you want to do is you want to get your cursor closer to the one we're dealing with. And they're going to ask some questions like left bound and right bound. What that means, so left bound, you just want your cursor to be somewhere on the left side of your crossing point here. So like left bound would be having our cursor like somewhere above it, because all of this stuff here would all be to the left of our intersection point. So as long as your cursor's somewhere in there where it's to the left of that crossing point, you're good to go. So here I'm just gonna take it, it's on this side, which is technically left, but I'm gonna get it a little closer to it. Maybe I'll go there because that's on the left of my intersection point. So I'll hit enter there. Then the next question it asks is right bound. So now what you wanna do is you want for the right bound, you want to be on the right side. Oops, that's not an R. You want to be on the right side of that crossing point. So you want your cursor somewhere below the line because all of that stuff would be on the right side of that intersection point. So here now for the right bound, I got to take my cursor below it and then hit enter. And then guess, we don't have to do anything on that because we've only got one spot in there that's relevant to us. So you can just hit enter again. And then it'll tell us there that our crossing point is at 3.1007811 when our y is 0 and our y is our height. So we could just put here for our height of 0 that our t is approximately equal to like 3.1 seconds. Okay, so like if that was 3, just be a little bit past the 3 seconds where it's crossing, which logically that probably makes sense. If you throw a basketball up, it's probably not going to be in the air super long before it comes back and it hits the ground. Okay, so that is the last example there. So you got that book page for tomorrow. So 398, 1 to 17. When you're on 15, skip letter D of number 15.